Okay, so this will be the last lecture for the course. We have only to finish this one section, the last section of Chapter 4. We've come back here at the end of the course to do the optimization stuff that we skipped the first time through. We've already finished 4.11 and 4.12. So 4.13, so this will be about global extrema. In fact, most of the ideas that we're going to be using in this section are methods that we covered in the two previous sections. So in some sense, what happens in this last section is all of these ideas come together and we see how they can fit together to find this global maximum value of a function. So now what is that? Here's a definition. A global maximum point of a function on a domain is a point A where the value of the function is at least as big or bigger than the value of the function at every other point on the domain. So you can see why we call it a global maximum. This is very often what you really are interested in. I mean, let's suppose the function f here represents profit and D represents a space of parameters that are at your disposal that you might choose between. Well, of course, you want to pick the parameters such that you find the absolute maximum value of profit, or whatever else it is that you're trying to maximize. And if it's a local maximum, local maxima are nice, they're interesting, but a local maximum that is not the highest local maximum, well, that's not really what we're interested in. Okay, so this is an important concept. The difficulty is that the ideas of calculus are defined, they're naturally thought of as local ideas. We look at limits as things get really small, and derivatives are defined very locally. So these calculus ideas are not very naturally set up to find global extrema, and that's a concern that we're going to have to face and deal with, and there's a big theorem that allows us to bridge that gap. Okay. So the first new idea I want to talk about is a way of breaking the problem down into smaller pieces, and these are what I'm going to call subdomains. I'm going to define a subdomain of a set to be a subset with the property that every point in that set has the same constraint equations. So let me show you an example of what I'm talking about. So think about the closed unit ball in R3. Now this is a natural set to talk about, not a particularly weird set. Let's draw a picture of it here. So, well, that's the sphere, so now I have to fill this in, So I'm trying to represent there the solid closed unit ball. Okay. Set of points where the distance to the origin is less than or equal to 1. All right, so suppose this is my domain, and I want to find the maximum value of some function. Well, the problem is that different points on this have different constraint equations. So what I'm going to do is I'm going to break this into two separate chunks. On the one hand, there's the sphere around the outside. That's the set of points where the distance to the origin is exactly equal to 1. And then separately, let's talk about the interior. That's the set of points where the distance to the origin is less than 1. And I claim each one of these is a subdomain, as defined here. Each one of these has the property that every point on each one of these sets has the same constraint equations. So let's see some specific examples. Let's look at, let's say, let me give you some pencil. Let's look at, say, a point in there, somewhere in the interior. Well, at that point, there's no constraints. You can move in any direction you want. Any one of those directions could be a velocity vector. So no constraints at all. Every point in this set has that feature, that there are no constraints. So subdomain. Okay. let's consider a point on the surface. Well, every point on that surface, now there are different tangent vectors allowed at different points along the surface, but every point on that surface has the same constraint equation, and that is that x squared plus y squared plus z squared is equal to 1. So, same constraint equations, and therefore this too is a subdomain. So now it's not always the case that you can do this. It's not true that every single set can be broken down into these, what I'm calling here, subdomains, but very often you can. And a nice thing happens when this works out, when you can break everything down into subdomains, and that's what we're going to talk about here. Okay. Here's another example. By the way, a little bit harder of an example, let's consider the unit square in R2, and here's a picture of it. So the unit square in R2 is all of this and all of the interior. Right. So now, can I break this up into subdomains? Well, sure, and here's the way you do it. Each vertex is its own separate subdomain. Each edge, that's each sort of open-ended edge, is its own subdomain. And then the interior. Every point in the unit square, the solid unit square, is on exactly one of these subdomains, and every one of these subdomains has the feature that all the points are similarly constrained. So for example, take E1 here. This edge, every point on that edge has the same constraint equation, namely y equals 1. Okay. Every point on this edge over here, E4, every point on that edge has the exact same constraint equations, namely x equals 0 for that one. Okay. Okay, so what is this bias? Let's think through what would happen if we're looking at a set, like let's say this one, and suppose that there is a global maximum of our objective function, f, somewhere on this domain. Well, if it's on this domain, that means it has to be on one of the subdomains. So let's say, arbitrarily, I'm going to say it's on this edge here. Maybe that's where f is maximum. So critically, though, it has to be on one of the subdomains. The set itself, our domain itself, is required, by assumption of your argument here, the set is the union of these subdomains. Okay, now, that absolute maximum, that global maximum value then, what can I say about it as it pertains to this subdomain? Well, it's the function is bigger here than anywhere else in the entire set. Well, certainly it would follow then that the function's bigger there than anywhere else on the subdomain. And it follows from that that point, the value of the function is bigger than anywhere nearby in that subdomain. And so what that means is it's a local maximum. If it's a global maximum of the function on the entire set, then it's got to be a local maximum on whatever subdomain it sits on. And that means it has to be a critical point on that subdomain. So, if we're looking for the global maximum value of the function, what we're looking for is something that we know is a critical point, and we already have methods for finding critical points. We have methods for finding critical points on each one of these subdomains. So I could go through all of the subdomains. Gosh, there's 9 of them here, come to think of it. I could go through each one of these subdomains, find all the critical points on all of these subdomains. This global maximum, if it exists, has got to be one of those critical points. So that's the idea. All right. Now there is a problem with this idea, and that is that if I find all the critical points and then I just do a comparison, plug in and see what the value of the function is at all these values and pick the one that's the biggest. That assumes that the absolute maximum exists in the first place. That is not always the case. So let's see some single variable pictures here. Here is a domain, and here is a graph of a function. And the way I have this function drawn, you can see that it has an asymptote on that line. And there is no global maximum value for this function. There is no global maximum point. No point in this domain achieves a value of the function that's bigger than all other values. And it's tempting to say, well, what about here? And the problem is the way I have this function drawn, the value of the function there is there. Which is, actually, it looks like it's smaller than all the other values. Not only is it not the largest, it appears to be the smallest. So, and then you say, well, what about some point closer, maybe, on the left side, but really close to it? Well, that's going to have a value up there, but there will always be some other value that's just a little closer to the asymptote and whose value the function then is higher. So there is no global maximum point of this function on that set. Okay. So that is a huge problem, and if you were to play the game here of looking for the critical points on all the subdomains, and then just plug in and see what the value is of the function for all those values, and look just direct comparison of those values, you would not find the global maximum because there is no global maximum. Okay, so all of this assumes that the global maximum exists in the first place. So the fact that this is not always true is a problem. So what we're going to have to settle for as consolation is a theorem here that says that under certain conditions it's true. So here are the conditions. These are important conditions. The objective function, we need to check that that's continuous. The domain has to be closed and bounded. Now, it's beyond the scope of this course, just slightly, not much. This is not a super hard theorem to prove, but we're not going to talk about the proof in this course. But the punchline of this theorem is that under those conditions, if the function is continuous, if the domain is closed and bounded, then the function does achieve a maximum value somewhere on the set. That absolute maximum value point is there. So under these conditions, continuous, closed, and bounded, it's perfectly fine to take this process that we've described and use that to find your maximum value point. We know it's in there somewhere. It's got to be a critical point on whichever subdomain it is. Find all the critical points, compare the values. Whichever one is the biggest has to be the absolute maximum value. Okay. Now, these three figures here are intended to show why these three conditions are essential. So, what goes wrong if the function fails to be continuous? What goes wrong if the domain fails to be closed, or if the domain fails to be bounded? So here we go. Now, I'm going to show you why these conditions are necessary. I'm not going to show you why these conditions are sufficient. Again, that's beyond the scope of the course by a little bit. So what happens if the function fails to be continuous? Well, that was this example we were looking at previously. If there's a discontinuity, and the example I have here is a discontinuity with an asymptote, then the function could perfectly reasonably approach infinity from one side. And then no matter how high up you go, there are always points that are higher. So there's no maximum. And that was made possible by the fact that we didn't require the function to be continuous. You can't have an asymptote in the middle of your domain if the function is required to be continuous. So continuity keeps that problem from happening. Okay. What if the domain is not closed? Well, here's an instance of a domain that's not closed. You can see there's a boundary point here that's not part of the domain. And that permits basically the same kind of a thing to happen, that the function can sort of run off to infinity toward that, what might be an asymptote there. And this function here, by the way, is perfectly continuous on that entire domain. Right? It's the fact that there is an open end that makes it possible for this continuous function to approach infinity, and thereby avoiding the existence of an absolute maximum. So again, this is also something that we have to avoid, and we avoid that open endpoint by requiring the domain to be closed. Okay, lastly, the domain has to be bounded. Well, here's what might happen if the domain is not bounded. Your domain might just run off to infinity, and there it's actually pretty easy to make the function approach infinity. It doesn't even have to do so asymptotically. It can just sort of increase at a linear rate, let's say. So again, there is no absolute maximum value point here, because whatever point you might pick, that value of the function can't be the biggest. There's going to be some value, some point in the domain, that unbounded domain, where the value of the function is even bigger. So again, we need to make sure that this is avoided. We avoid this by requiring that the domain be bounded. Okay. All right, so let's apply our new strategy and our new tool to an example. Now, this is an example we have already looked at. We looked at this in the previous section. We looked at this function, and we were on the ellipsoid defined by this equation. So we've already gone through and found 6 critical points, and these are they. So what do we do with those 6 critical points? Well, in the previous section, we just called them critical points and sort of threw up our hands. We don't have a way of identifying even so much as whether these are local maxes or local mins. But certainly in the previous section, we didn't talk about how to determine if these are, whether any of them might conceivably be a global max or a global min. Okay, so our new theorem is what's going to allow us to do this. Our new theorem, we take advantage of the fact that this ellipsoid is closed and bounded, and our function, our objective function, is continuous. So the theorem on the previous page tells us that this absolute maximum point that we're looking for, the point on the ellipse, hopefully, which finds the absolute maximum value of this function, must be there somewhere. Knowing that it must be there somewhere, we look at our existing critical points, so we know, in fact, that these are the only possible points that could be even local maxes, much less the global max. The global max exists, therefore it's got to be one of these. So we take these points, take these 6 points, and just plug them into this function. And see what values you get. And those are the values you get. So the absolute maximizer, it's got to be one of these points, one of these 6 points. Here are the values of the function at those 6 points. And it follows at a glance that these 2 points, so those 2 points there, are your absolute, your global maximum value points. And then the absolute maximum, the global maximum value of the function is 36, achieved at these 2 points here. Okay. All right. Now that sort of finishes off that example from the previous section. Let's see one now where we have to break it up into pieces. We'll use subdomain, so we're going to consider this function. And you'll notice that's a continuous function. We're going to consider that function on the closed unit ball in R3. We considered that at the start of this lecture, and we can break that closed unit ball in R3 down into two pieces. There's the interior piece, and there's the boundary piece. And these are subdomains in the sense that each one of these, all the points on individually each one of these subdomains share the same constraints. Okay. All right. So as we just observed, this function is continuous, and this domain, well, we didn't say so, but let's say it now, the domain is closed and bounded, and therefore the maximizer that we're looking for must exist, and so we can proceed with our method. So in other words, we're going to look on each of these subdomains. One at a time, we're going to look at these subdomains, find the critical points on those subdomains, consider them all, and the absolute max has got to be one of them. We'll just consider the values of the function. Okay. So let's take these one at a time. We will look at D1 first. All right. So I guess I'll leave this all on the screen. D1, there's no constraints, so we're just going to take the gradient, set it equal to 0. I guess we have to worry about differentiability. Conveniently, the function's differentiable. No problem there. So we take the gradient and set it equal to 0 and solve. Well, the gradient of f is 1, 2, 3. When we set that equal to 0, how will we solve this equation? Are there any points that make 1 equal to 0 and also make 2 equal to 0 and simultaneously make 3 equal to 0? Well, this is nonsense. Of course not. Clearly, 1, 2, 3 cannot equal to 0, 0, 0. So what that means is that there are no critical points on that subdomain. Right. So now let's look at this second subdomain. Well, this is going to be a Lagrange problem. All the points on this domain have a single constraint. So we're going to apply the method of Lagrange multipliers. Again, we'll consider consider differentiability. The objective function is clearly differentiable. That's clearly differentiable. The degeneracy condition requires looking at the constraint gradient, which is this. Let's rewrite our constraint equation as x squared plus y squared plus z squared equals 1. Whoops. That's equivalent to this constraint. And so this constraint gradient, where is this constraint gradient equal to 0? Where does this happen? Well, now that does happen, right? These coordinates, so x, y, and z could all equal to 0. So in other words, we could look at the origin. The problem is that the origin doesn't satisfy that equation. So what we found is a point that satisfies the degeneracy requirement, but it's not on the set for which we care about the degeneracy requirement. So there's not a critical point, and we just get to ignore it. So there are no degenerate critical points. Okay. So lastly, we have the Lagrange condition. Here is our objective gradient. Here's our constraint gradient. This is the Lagrange condition, which I'm going to rewrite over here as 3 separate equations. Now don't forget that the Lagrange condition matters only where the constraint is satisfied. And so altogether we have 4 equations and 4 unknowns to solve for. And so this is a problem similar to one that we've seen before. You can solve for lambda in all 3 of these equations and get certain relationships between x, y, and z. You can plug those relationships into the constraint equation and solve for x. thus giving you those values for x. Once you know x, then this tells you y, and this tells you z, and so these two values of x give you 2 critical points. Okay, so altogether then, we found a grand total of 2 critical points. In the interior, the first subdomain we looked at, there were no critical points. In the boundary, there were no degenerate, there were no differentiability failures, and so all we have is these Lagrange critical points. Now, we know the absolute maximum has to exist. We know it's got to be one of these critical points, so we just take these points, plug them into the function that we're trying to maximize, which again is that. And these are those values. So this point is our absolute maximum point. There we go. Okay. All right, so one last example. Mostly I'm going to show this one to show a combination of circumstances that can arise. We're going to find that it ends up getting seemingly very complicated, but it also at the same time is actually ends up being pretty simple. So here we're going to look at this function. There's our objective function and our domain, the unit square, and let's see, what can we conclude about can we find a global maximum? So the very first thing I'll observe is that the objective function is continuous, the domain is closed and bounded, and so by our theorem, that we discussed earlier in this lecture, that means that the absolute maximum point, at least one, must exist, so it's out there somewhere, and we can proceed with our subdomains argument. So let's take these one at a time. We'll start with the interior. Well, the interior, there are no constraints, so we just take the gradient, set it equal to 0, and solve. And there's only one point where it can equal to 0, that it is. So now, is that a critical point? Do we call it a critical point? We don't, actually, because it's not in the interior. Let's look very carefully at this point, 1/2, 0. Well, that point, x equals 1/2, y equals 0, is there. It's on this edge. It's on E3. We were describing conditions for finding critical points in the interior, and we got a point which is not in the interior. So it doesn't matter. We throw it away. Alrighty, so it does not count as a critical point, an interior critical point. Alright, let's look at the top edge. By the way, let's sort of sanity check this problem. We're going to have to check the top edge and then the right edge, and then we're going to have to check the bottom edge and the left edge, and it looks like we have a bunch of problems here. And then we have 4 vertices. Grand total, let's not forget, we have 9 subdomains here. So it seems like this could get out of hand. But the good news is, and you'll notice as I pass through this, that each one of these goes down pretty quickly. I mean, the equations that you write down for each one of these subdomain problems, not that bad. So the bad news is lots of subdomains. The good news is they're all easy little questions. So let's take them one at a time now. Maybe I'll just do some of these. Let's take the top edge. So there's a single constraint. So this is a Lagrange problem. There's the constraint. There's the equation describing those points. So that's the function. That's our gradient function. Here's the constraint gradient. And our objective gradient. If it has to be some multiple of that constraint gradient, then you get these 2 equations. Now again, let's not forget that those equations only matter on this set, on that top edge. So that is also in there. And now grand total, we have 3 equations and 3 unknowns, and solve. And the good news is that this is very straightforward. I mean, there's hardly anything to do. In fact, look at this. That tells you what y is right there. And what's x? Well, solve that little simple equation right there. So you get a critical point. All right. It's similarly convenient for the right edge, the bottom edge, and the left edge. Similar details, and the listener can read through and follow those independently. All right. Now, the last thing I'm going to talk about is those vertices. Each one of those is, I suppose, its own little subdomain. Now, you could write down constraint equations and go through the whole process, but these are actually really easy. You don't even have to resort to the methods of Lagrange constrained optimization. Now, keep in mind, all that constrained optimization is doing is helping you find possible tangent vectors that might allow you to eliminate a point as a possible maximum. So we're considering now a set that consists of a single point. Now, what possible tangent vectors could I have on a single point? Well, there are no tangent vectors because there's no direction that you can move as a velocity of a curve and remain at that single point. So there's no tangent vectors. That means that there's no possible way that you can eliminate this as a possible maximum, and therefore this remains a possible maximum. So you could call that bad news, I suppose, but I like to call this good news. It's good news because what it says is that when you have a single point as a subdomain, you don't have to do any analysis. You just label it a critical point and walk away. There's no tangent vectors, no way to eliminate it. It remains a critical point. So similarly, that's a critical point, that's a critical point, that's a critical point. So freebies. So grand total then, with all of the various subdomains taken together, here are all the critical points. Plug them all into the function. These are the values of the function at all the critical points. We know the maximizer's out there somewhere. We know it's therefore got to be a critical point. These are the only critical points. Therefore, the maximizer's got to be one of these points. And the function is biggest among these values at these 2 points, 1, 1, and 0, 1. So those are your absolute maximum values. Okay, so that's it for 413. And yeah.